Yeah.
Okay. Thank you. So thanks everyone for coming to this second invited presentation session. So we will have two small talks which are recording videos. Don't hesitate to start asking your question in the Q&A part at the bottom of your screen so that the speaker can see those questions. They will answer to them at the end of the video. So we will start with the presentation made by Aline Gemin, which is a work she did with Thomas Brouillet on subgame perfect equilibria in turn-based reachability timed games.
Yeah, please note that the session will be recorded. And so if the speaker have a problem with them, because the session will be then put online, so just tell me in the chat if there is a problem with that.
Hello everyone, this presentation is based on a paper entitled on subgame perfect equilibria in turn-based reachability time games. This is a joint work with Thomas Brouillet. First, I'll present some context and I will introduce all the concepts I need to explain what is the problem that we have studied. This problem is a decision problem that we call the constrained existence problem. At the end of my talk, I will explain how to decide this decision problem. But first, some context. In our everyday life, systems interact with their environment. But with critical systems, bugs may have dramatic consequences. For this reason, it is crucial to ensure that a system is correct and satisfies some properties. One way to do so is program testing, but as the extra-site testing shows the presence but not the absence of bugs. In order to prove in a mathematical sense that a given system satisfies some property, formal methods have been introduced. With verification, we have to give a formal description of the system thanks to a mathematical model and of the properties that the system has to satisfy. Then we check if the system satisfies the properties or not. With synthesis, we want to build a system which is correct by construction. And a way to do so is to use games played on graphs. And in particular, two-player zero-sum games played on graph. What is a game played on a graph? The arena of the game is a graph, and we have two players. So the round player will represent the system, and the square player will represent the environment. The round player owns the round vertices, and the square player owns the square vertices. But how do we play in such a game? It is a turn-based game, so we assume that there is a token in an initial vertex, or in the vertex v0, and the player who owns this vertex has to choose an ongoing edge and move the token through this edge. So now the token is in a new vertex, and the player who owns this vertex has to choose an ongoing edge and move the token through this edge. So now the token is in a new vertex, and so on. This leads to an infinite path in the graph that we call a play. You also have to define the objectives of the players, the goal of the players. Here, the system wants to satisfy a property, and the goal of the environment is to avoid that. In this talk, I will assume that the objective of the players is a reachability objective. So here, the round player has a reachability objective. That is that he has a subset of vertices called his target set that he wants to reach, to visit. So in this example, the round player wants to visit the vertex v4. We have that the system satisfies the property if and only if the round player has a winning strategy. The round player, so the system has a winning strategy, means that he has a way to play such that if he follows this strategy, if he follows this strategy, he will win whatever the behavior of the other player, so whatever the behavior of the environment. So with synthesis, we want to find this winning strategy. This system, this setting is too restrictive. And so we can, for example, consider multiplayer games, so game with more than 2 players, or to consider real-time features. The arena of the game is now a timed automaton. If we consider these two features, we obtain a multiplayer time game. But first of all, we will focus on reachability multiplayer games. In this setting, we have 2 or more players. In my example, I consider the round player and the square player. And the objective of the round player is to reach the vertex v4 as before. But now the round player wants to reach the vertex v4. So in this setting, the behavior of the players is not antagonistic. For every place or for every infinite path in the graph of the game, we can compute the gain of the players. So for example, if I have the play row and I want to compute the gain for the round player, he will obtain a gain of 1 if he visits his target set along this play. And we will say that he wins, and otherwise he will obtain a gain of 0, and we will say that he loses. In the same way, we can obtain the gain of the round player, the square player, sorry. For example, if we consider the play v0, v1, v0, v1 infinitely often, no player visits his target set, and so they have both a gain of 0. But if I consider the play v0, v2, v3, v0, v2, v4, and we loop in v4, both players visit their target set, and so they have both a gain of 1. Notice that this is a qualitative objective, so we do not take into account the number of steps it takes for a player to reach his target set. A strategy for a player is a function that assigns the choice of a player when it is his turn to play. In my example, I only consider memory-less strategies, but you can consider strategies with memory. When we fix a strategy for each player, we have a strategy profile. And when we have fixed a strategy profile on an initial vertex, there is only one play which is consistent with the strategy profile from this initial vertex. And we call this play the outcome of the strategy profile. So here, for example, I have a strategy in blue for the round player and a strategy in red for the square player. And if I follow these strategies from V0, I obtain the play, the outcome V0, V1, V0, V1, V0, V1, and so on. In the setting of two players awesome game, we study the notion of winning strategies, but in the setting of multiplayer games, we study the notion of equilibria. The most notion of equilibria is the notion of Nash equilibria. A strategy profile is a Nash equilibrium if no player has an incentive to deviate unilaterally. That means that if I am the round player, and if I know the strategies of the other players, I have no incentive to change my way to play if I assume that the other players will follow their own strategies. So here is a counterexample. So a strategy in blue for the round player and a strategy in red for the square player. We've seen that the outcome of the strategy profile is V0, V1 infinitely often, and that the gain of both players is equal to 0. And it is easy to see that from V0, the round player should go in V2. Indeed, in this way, the outcome is now V0, V2, V4. And so the round player visits his target set. He has a gain of 1, and 1 is better than 0. So it is a profitable deviation for the round player. That means that the strategy profile dark blue and red is not Nash equilibrium. And this strategy profile is a Nash equilibrium. So the difference is here. So the square player chooses to go in V3 instead of V4. The outcome of this strategy profile is the same as before, so both players lose, but it is a Nash equilibrium. Indeed, even if the wrong player chooses to go in V2, the square player always chooses to go in V3, so the wrong player will never reach his target set. And so he will always obtain a gain of 0. And in the same way, for the square player, even if he changes his strategy, the outcome of the new strategy profile will be V0, V1, V0, V1 infinitely often. And so the square player will obtain a gain of 0. And so this is not a profitable deviation. So this strategy profile is a Nash equilibrium. But you can say from V2, the square player should choose to go in V4 and to reach his target set. And this is what we call an incredible treat. And a way to avoid incredible treat is to consider subgame perfect equilibria. A strategy profile is a subgame perfect equilibrium if it is a Nash equilibrium in all subgame. It is easier to apprehend this notion if we consider the unfolding of the game. So the game begins in V0, and from V0 you can go in V1 or in V2. From V2 you can go in V4 or in V3, and so on, and you obtain an infinite tree. And all the subtrees of this tree are called the subgames of the game. And the strategy profile is a subgame perfect equilibrium if it is a Nash equilibrium in all test subtrees. So we have seen that this strategy profile is a Nash equilibrium, but this is not a subgame perfect equilibrium. Why? Because if we consider this subtree, so this subgame, and if the players follow the fixed strategies, they don't visit their target set. But from V2, the square player can choose to go in V4 and to visit his target set. And so he has a profitable deviation. That means that there is a profitable deviation from V0, V2. And so this strategy profile is not a subgame perfect equilibrium. In multiplayer reachability games, different equilibria may coexist. And it's the reason why we consider the constraint existence problem. What is this problem? We have an upper and a lower threshold for each player, so either the value 0 or the value 1, and we ask, does there exist an equilibrium, a Nash equilibrium or a subgame perfect equilibrium, such that if all the players follow this equilibrium, the gain of each player is between is fixed thresholds. It is proved that this problem is NP complete for Nash equilibria and P space complete for subgame perfect equilibria. Notice that there is a complexity gap between Nash equilibria and subgame perfect equilibria. Okay, so now timed automaton. During my talk, I will assume that you are all familiar with the notion of timed automaton, but just very quickly. Here is an automaton, and so we have states and we have transition, and we want to reach this smiley, so this location. Here is a timed automaton, so we add clocks and we add guards on the transition. That is that the clocks have to satisfy the guard if we want to take this transition. We can also reset clocks, but it's not the case in this example. The semantic of a timed automaton is given by its infinite transition system, something like that. And it is well known that we can consider the abstraction of this transition system given by a time abstract bisimulation. And in this way, we obtain the region graph. And this region graph is finite, but has a size exponential in the size of the timed automaton. Okay, so now we know what is a multiplayer reachability game. We know what is a timed automaton, And now we can define a reachability timed game. In this setting, we have a timed automaton, but we have a partition of the locations between the different players. And additionally, each player has his own target set that he wants to visit, that he wants to reach. And we call this model a partition timed automaton. The semantic of this partition timed automaton is an infinite turn-based reachability game. And how do you obtain the graph of this game? It is as for timed automaton. So this graph is the associated transition system of this timed automaton. And then you have to define the partition of the vertices between the players, but it is easy. So for example, here, the underlying location is the location L0, and the location L0 is a location of the round player. So this vertex is a vertex of the round player. In the same way, we define the target set of the player. So for example, as L4 is in the target set of the round player and of the square player, this vertex is also in the target set of the round player and of the square player. And we call this infinite reachability game a reachability time game. Notice that all the notion I have explained before, so the notion of strategies and Nash equilibria and subgame perfect equilibria, holds in this setting. So we can consider question about the existence of Nash equilibria, the existence of subgame perfect equilibria, and in particular, we can study the constraint existence problem. So now we give a partition timed automaton and a lower and upper threshold for all the players, and we ask does there exist a Nash equilibrium or a subgame perfect equilibrium in its associated reachability time game, such that the gain of the players are between the fixed threshold. It was already proved that this problem is X-time complete for Nash equilibria, and we have proved that this problem is also X-time complete for subgame perfect equilibria. And the purpose of this talk is to explain this result. You can notice that in this setting, there is no complexity gap between Nash equilibria and subgame perfect equilibria. But how can we decide this problem? So we know that deciding the constraint existence problem in finite reachability games is p-space complete. But here, the reachability time game is infinite, so we cannot use this approach. So first of all, we will transform the reachability time game into a finite reachability game that we call the region game. And how do we obtain this region game? In fact, the game graph of this game is obtained as for timed automaton, and we use the notion of time extract simulation and the notion of region. And so we obtain the region game, which is a finite reachability game, but which has a size exponential in the size of the partition timed automaton. Okay, so now if you want to use this region game, we have to prove that it is equivalent to consider the existence of a subgame perfect equilibrium in the reachability time game and in the region game. What do I mean by that? We have proved that there exists an SPE in the reachability time game, so in the infinite game, with a given gain profile, if and only if there exists an SPE in the associated region game, so in the finite game, with the same gain profile. So one can decide the constraint existence problem in this region game. Okay, let's start again. Let's try again, sorry. We know that deciding the constraint existence problem is in finite reachability games is p-space complete. The region game is a finite reachability game, but the graph of the region game has a size exponential in the size of the partition timed automaton. So naively, we obtain an X-space algorithm, and we want to obtain an X-time algorithm. So we have to find another algorithm, an X-time algorithm, to decide the constraint existence problem in finite reachability games. I will not give the details in this talk, but it is based on an SPE outcome characterization inspired by the one used in quantitative reachability games. The running time of this algorithm is exponential in the number of players, but not in the size of the game graph. And so to summarize, we have an algorithm to decide the constant existence problem in finite reachability game in type complexity exponential in the number of players, but polynomial in the size of the graph of the game. We have that the graph of the region game, which is a finite reachability game, is finite and has a size exponential in the size of the underlying timed automaton of A. And we have that deciding the constraint existence problem is equivalent in the reachability time game or in the region game. And so we have an algorithm to decide the constraint existence problem of SPEs in reachability time game that runs in exponential time, both in the number of players and in the size of the underlying timed automaton of A. So to conclude, in this talk, I have explained that the constant existence problem of SPEs in reachability time games is in X time. Up to our knowledge, it's the first time that SPEs are studied in this kind of setting. It is interesting to notice that there is no complexity gap between Nash equilibria and subgame perfect equilibria in this setting. Our results are based on this following result. If there exists an SPE with a given gain profile in the reachability time game, there exists an SPE with the same gain profile in its associated region game and vice versa. And it, in fact, will prove a more general result, that is, given a B simulation equivalence on a game which respects some good properties, we prove that the same result between the game and its we prove the same result between the game and its quotient game. And we hope that it will allow us to handle other kind of objectives. Thank you for your attention.
Thanks for the presentation, Aline. A bit delay. So for starter, do we have any question by the public? So if so, you can write it in the questions or raise your hand so that I can allow you to speak. Considering there's nothing, I will start for now. It's more about the other objectives that you point at the end of your presentation. The kind of behavior that you can get in your subgame perfect equilibria can create some Zenon behavior where the players do not let the time pass. Do you have any idea how to force to change the objective, to change your approach, to force the players to let time elapse during the game?
I don't understand your question.
I'm sorry. So in time games, it often happens that we have some Zenon behavior where a player plays a smaller and smaller increment of time, and so the time does not elapse for a while. And I was asking whether you can adapt the algorithm that you have in order to force the players to let time elapse. So that's why I was saying it's a different kind of objective here.
Yes, indeed, we don't take into account the Zenon behavior in your paper, but we hope that approach, like I don't remember the paper, but they change the objective to take into account the fact that a player cannot have an infinite number of action in a finite number of time, I think, but I don't remember the details. But we hope that this kind of other objective can be used in our approach.
Do you have any idea of the kind of properties that are needed for your for other objectives to work in your approach? For instance, objectives that can work with a region graph or something like that?
Yes, here, for example, it works for parity games, for we need to have that two B simulator place have the same gains in the infinite game and in the region game, and it should be the case for parity game. But it's only to have to obtain the theorem about the fact that there exists an SPE in the infinite game with a given gain profile, if and only if there exists one in the region game with the same gain profile. Then one need an approach to decide the constraint existence problem.
Nice. I'm just looking. So there is a question from Benjamin Montmege who said, for the last step of your X-time algorithm for SPE, do you think that zones could be used instead of region in order to be more practical from an implementation point of view, avoiding having to build the whole region game a priori?
Thank you for the question, Benjamin. I'm not familiar with the notion of zone, but so I don't know if the properties hold with zone and if it will be it will be a better way, a better abstraction in practice. I don't know.
Okay.
Sorry.
That can be discussed more in details a bit later. I think we will move on to the second presenter now. So the second presentation is from Radoslav Piorkowski, which is doing a PhD in Warsaw, and he's presenting a work that is done with Lorenzo Clemente and Slavomir Lazota on time games on deterministic separability. So let us start this video, hopefully.
This video relates to the synthesis problem proposed by Alonzo Church. We brought it to the world of timed automata in our paper presented at the last year's ICALP conference. My co-authors are Lorenzo Clemente and Sławomir Lazota. We all work at the University of Warsaw in Poland. I am Radosław Piorkowski, and this is Timed Games and Deterministic Separability. In the last year's ICALP presentation, which some of you may have already seen, I have answered three following questions about our work. Firstly, what is the problem we solved? Next, what was the novelty of our work? And finally, why do we think it can be useful? Here, since I am dealing with a more specialized audience, I will be enticed to additionally provide a sketch of the proof of our most important theorem. But one step at a time, let's start with the answer to the first question. So, what did we do? In short, we brought the Church's synthesis problem to the setting of timed automata and proved an analog of the famous Bichy-Landweber theorem. Before I can tell you how we designed our adaptation, let me introduce you to the standard variant of the Church's problem. It was first stated by Alonzo Church in 1957, and now many see it as the cornerstone of the program synthesis. It takes the following form. Given a specification of some kind, we ask if there is a controller which, for every possible input, will produce results matching the specification. I will present it visually the following way. We are given the green machine representing the specification. It is fed with an infinite word of pairs of letters, and it reads it symbol by symbol. Finally, when the whole infinite word has been read, it answers either accept or reject. But this is just a part of our system. In fact, the initial input stream consists only of a single string of letters, and a controller resides in the middle. The controller is a very simple machine, a letter-to-letter transducer, or, if you prefer, a deterministic automaton with an output. Based on the input letter it has just observed, and on its internal state, it produces a new letter of the upper string. As you can see, it operates on the letter-to-letter basis. That is, for each letter of the input, there's exactly one letter of the upper string produced. So once again, the Church's problem asks if a purple controller exists which can make the specification accept no matter what the initial input stream was. In case there exists one, we want to construct it. We can also look at this problem from the point of view of game theory. Then we are dealing with what is called a synthesis game. Such a game has a winning condition and two players, controller and the input. In a single turn of this game, the input player produces a single letter and the controller responds to it. In such a formulation, the solution to the church's problem is just a finite memory strategy for the controller. A landmark theorem by Bichy and Landweber says that if the winning condition is given by an omega regular language, we can decide if the strategy for the controller exists. What's more, if there exists one, we can also synthesize it. As I mentioned at the beginning, in our paper we generalize the church's synthesis to the setting of timed automata and prove an analog for the Bichy-Landweber theorem. Now, let me show you how we add time to the synthesis games. The adaptation is quite straightforward. We replace the models with their timed counterparts, that is, finite omega automaton is replaced by timed omega automaton, while finite transducer is replaced by a timed transducer. Let me illustrate that visually. The changes appear in three places. First, the input becomes a timed word. Input player now produces letters associated with a timestamp. He may place a letter on an arbitrary position to the right of the previously played symbol, for example here. Now the controller needs to wait a moment before it sees the next letter. An important remark to make here is that those machines do not access the timeline directly. They don't see the exact time values of the input symbols. For this reason, they need another way of measuring time. That's why we give them clocks. For simplicity, in this video I chose to give them one clock each, but in general, these machines can have arbitrary number of clocks. What does a clock look like? It has a hand which moves as the time flows, and the owner of the clock may measure the time relative to the integer values written on the face. In this example, the owner knows that the hand is somewhere between 3 and 4, but the exact time value is unknown. Additionally, when the measured time exceeds maximal constant written on the clock, in this case 6, the hand stops, and from that point on, we only know that at least 6 seconds have passed from the last reset. How can controller use the readings from the clock? The controller's strategy is just a deterministic timed automaton with an output with transitions of the following form. This transition says that in the state P, if the clock value is between 5 and 6 and the input symbol is A, we output X and go to the state Q. The transition may also decide to reset a clock, that is, to set its value back to 0. Take a look at this example. Assume that the controller has just reset the clock. Now, the clock measures the flowing time. The controller only stops when it sees the next input letter. In this case, it can read that the time is somewhere between 5 and 6. Now he may use that information to decide what letter to produce next. To sum up, the timed games have three differences from the original ones. Player input can play timed symbols, and both machines here are given clocks, and they perform timed transitions that speak about the values of the clocks. This is how our timed synthesis games are defined. Before telling you exactly what we proved about them, I need to be a bit more formal. Let me state the synthesis problem for the timed games. Once again, we are given a specification, which is now a timed omega regular language, and our objective is to construct a winning strategy for the controller player, if it exists. However, we need to make a few new design choices because of the addition of time. First of all, now we may wish to specify whether the winning condition describes desired or undesired behaviors of the controller. This was not an issue in the original setting because we dealt with omega regular languages, which are closed under the complement. Unfortunately, it's not the case for timed automata. Therefore, we may want to use a condition that tells us either when controller loses or when controller wins. The other choices are related to the clocks of the controller. Remember that we want to synthesize a timed transducer that uses clocks. We may wish to fix the number of those clocks in advance or leave that unspecified. And similarly, the clocks count up to some constant m. We may want to specify that in advance or quantify that constant existentially. Before I can tell you which choices we made here, it is best to mention the previous advances in this area. So in fact, the answers to the first two questions intertwine. Let us construct a table summarizing some of the possible choices. As columns, we'll have the type of the winning condition we use. The additional column here, deterministic, is simpler because the deterministic timed automata can be complemented. The rows correspond to the choices about clocks. We analyze the following three. When both numbers are fixed, when only the number of clocks to be used is fixed, but the clocks may count up to arbitrarily high constants, and finally, when no constant is fixed. The first of the known results is the decidability of the simple case when both numbers are specified up front and the winning condition is deterministic. Later, two other decidability results were shown, together with three undecidability results. As you can see, the second row was not considered before, but its first two cells can be easily filled up as follows. Our model is essentially a slight restriction of the setting of de Souza-Madhusudan, so our results belong to the last column of this table. The first one, a kind of byproduct, resides here. Our games are a bit simpler, so actually the previously known result is stronger. However, our result has a simpler proof. For the same reasons, our undecidability result in the last row is stronger than the previous one. Finally, our most important contribution resides in the middle row. We can decide the winner and synthesize the controller when only the number of clocks is fixed, but the constant to which the clocks count up to is quantified existentially. This result was not known before. By now, you should have some intuitions about what the answers to these two questions are. Now I will present you with a sketch of the proof of our main result. I will hide some of the technical difficulties, yet you should get a pretty good understanding of our construction. Formally, the problem we want to solve is as follows. We are given a game G, which is defined by a non-deterministic timed automaton recognizing its winning condition. Similarly to the Bicheland-Weber's theorem, the question is about the existence of a finite memory strategy for controller. However, in the timed case, there are two variants to consider, depending on whether we want to bound the maximal constant the clocks can use or not. Let's focus on the easier problem for now. Its proof has two steps. In the first step, we produce a game G2 with the same winner as G, but enabling clockless strategies for controller. Next, we produce a game without time at all. This completes the proof because the Bicheland-Weber theorem can be applied to G3. In the first step, we want to ensure that the controller wins in G if and only if he wins in G2, but without using clocks. We remove clocks one by one. Let's see how one such removal can be done. We start with a game G and ask about controller's strategies using, say, 3 clocks. We begin by copying G. We want to take one clock away from the controller. To make up for that loss, we introduce a special protocol for him. He will use that protocol to retrieve information about time. We begin the construction by updating the alphabets. Let sigma and gamma denote the old alphabets of players. New ones are built around those, but additionally contain an epsilon symbol and binary flags REQ and RSP, which stand for request and response. We force players to play according to the protocol by adding some extra requirements to the winning condition. But how does the protocol look like? In the original game, controller may have used a clock to retrieve some information about time. For example, he could have reset a clock here, measure something between 2 and 3 when the input played the next symbol, and finally, he would read 5 here. Based on that information, he could make strategic choices. In the modified game G', the controller must be able to do without the clock. He can make a request instead. The input player is obliged to respond to that request after exactly 1 second. When the controller gets the response, he may place another request. When the non-epsilon letter finally arrives, controller knows that more than 2 seconds have passed because he has seen 2 responses already. The protocol continues, and lastly, we know that precisely 5 seconds have passed from the initial request. Observe that with that protocol, controller could obtain the same information that the clock would give him. One requirement we impose here is that such chains of requests cannot be longer than the maximal constant from the clock, which is 6 in this case. It turns out that any strategy using clocks in G can be simulated in G' with the help of the protocol, and vice versa. Therefore, we know that both games have the same winner. Recall that we are talking about the variant of the problem in which the maximal clock constant is specified. It turns out that the only adjustment we need to make to lift this requirement is here. We may ask for request chains of finite length, and the magic of finite memory determinacy will do the rest. So, that was the first step of our proof. The second one is even simpler, as we only replace the winning condition with its untiming. It turns out that this is precisely what we need to wrap up the proof. As you could see, both problems here have essentially the same proof. The only difference lies in the requirement for fixed length or finite length request chains. Now, as the last part of the presentation, let me briefly tell you why we think our results are useful. Here, the answer is because they allow us to solve another interesting problem about timed automata, that is, the deterministic separability question. What is deterministic separability? It's a straightforward and natural problem. We are given 2 timed automata A and B, which are non-deterministic and their languages do not intersect. We ask if one can construct a simpler, deterministic automaton that separates the languages. That is, it includes the language of A, but is disjoint with the language of B. Now, using the results from the table, we may solve the corresponding separability questions. Observe that the separability problem without fixing any of the resources is still open, because the undecidability for games does not transfer to the separability question. We solve the separability with a simple timed game. The actions of the controller player are very limited. He can only play accept or reject symbols. Conceptually, he wants to prove that he knows some separator. To this end, he classifies the prefixes of the input word based on whether they belong to the read language or not. The specification, in turn, describes the undesired behaviors of the controller. For separability, there are 2 such cases. Either something that should have been accepted wasn't, or something that shouldn't have been accepted was. It turns out that this simple game characterizes exactly the separability question. Now it's time to summarize what I have told you in this video. First, I showed you how we generalize the Church's synthesis problem to a timed setting, and I sketched the proof of our main result. Later, I explained how our results relate to the previous developments in the field. Finally, I explained how our results about timed games solve the separability question. Should you wish to learn more, please visit my webpage here. And for now, thank you for your attention.
Thank you, Radislav, for the very visual presentation. Do we have any question for the public right now? Or should I start? Okay, so we don't have any right now. In order to understand, we start. In order to understand a bit more your results, you're able to build this controller when you have a fixed number of clocks that is given to you, but that number can be arbitrary. So in a way, for the deterministic separability problem that you tackle at the end, you've got some semi-decidable algorithm to deal with it in the full case, which would be to try to look for controller with that many clocks and then increase it. Okay, I understood. Okay, I just see. No, it's not a question. Okay, so that was the one thing that I wanted to make sure first. The second thing is, so you say the undecidability that you have in the synthesis cannot be transferred to the separability problem. Is there some strong reason for this separation? Is there some meaningful difference between the two problems that say you cannot try to do this same kind of undecidability proof?
So actually, the synthesis is just a more general problem than separation. Separation is just one use case, and it's. I mean, we couldn't find a way to do similar undecidability proof using this separation framework. We needed.
But there is no clear argument. It's more.
No, there is not.
Okay. See, Benjamin asked a question again, so let's turn to him. What happens if the controller is allowed to use arbitrarily many clocks with different granularity as the objective time automaton, for instance, using guards of the form x smaller than 1/3?
I'm not sure because we did not consider this different granularity. Perhaps some answer could be given here, but I would have to think about it. I cannot answer this question right now.
Question about the question, potentially I will give the allow Benjamin to speak also. What would stop this just to blow up the granularity by multiplying by the least common multiplying it so that everything goes back to granularity of 1?
Yeah, perhaps it is a good solution, but I would have to just think about it.
Okay, sorry. So
maybe Slavek can add something. Can you?
I'm trying to find him, but yeah.
Sławomir Lasota.
Yeah, I just added him. So maybe, yeah, if you want to speak, you can.
Hello, do you hear me?
Yes.
I'm not sure exactly, but I guess once the size of the controller, number of transitions, number of clocks, etc., is unknown, then the trick of multiplying everything by a maximal constant, right? It kind of doesn't work, right? Because the controller is still unknown, right?
Yeah.
If I understand well the question, that would be my like first attempt to answer, but maybe we could go offline. I mean,
yeah, no, I was clearly thinking of a fixed number of clocks with the non-granularity, but yeah, you're entirely correct.
But is this granularity fixed in advance, or it's also a new parameter? Is this 1/3 fixed on the input?
This could be a parameter, and if I remember well, this seminal paper of Souza and Madhusudan, I guess they considered this kind of parameter as well, like something like granularity. But I may be not correct, not exact here.
So maybe. Maybe we're already 5 minutes into the break, so I would say, if possible, we move the last question on discussion on this topic to off.
Offline but online.
Offline, yes. So thank you very much to the speakers and to the organizer of this session to make it and to everyone that asked a question. And well, let's take a break, I guess, and stop this